Hey, it's Miss Wesley. It's Calc time, and today we get to talk definite integral applications. So, all the stuff we've been doing lately with taking an integral and evaluating it at certain spots, I want to see how we could put it into some more real life context with you today. We're looking at definite integrals packet, page 23, the Michael Jordan page, and at the top, you'll see the little cute dancing ballerinas. I would have started the lesson today with a joke, and I would have told you a construction joke, but I'm still working on it. Example one, at a certain factory, marginal cost, I want to underline that marginal cost is this expression, 3 times Q minus 4 squared. What is Q? Production level is Q units, how many units they're producing. By how much will the total manufacturing cost increase? So how much is the cost going to go up by if production level is raised from 6 to 10 units? I don't know if you see little hints in the wording of this problem that indicate that you're given a derivative, first of all. We should talk about that. How do we know that this isn't an original cost function? It's a derivative. Well, that's what marginal cost means. That vocab word means rate of change in cost. So if I called cost C here, this wouldn't be C of Q. This would be the rate of change in cost. This would be C prime of Q. What else? This is important. Dollars per unit. When you're given units that are something per something, you know that's a tip off that you're given a rate of change. Also, this thing I underlined at the end, production levels raised from 6 to 10 units. I wonder if that makes you think of a definite integral, like we're going to evaluate something from 6 to 10. And it does. If this is the rate of change in cost, we could get original cost values because we basically want a difference in the cost at producing 10 units and the cost at producing 6 units. So in math, we could write that as C of 10 minus C of 6. That's what we really want. Isn't that sort of kind of the final step to a definite integrals question? If we could integrate the original derivative, 3 times q minus 4 squared dq, because we want to integrate with respect to the variable q, and if we could integrate it from this value to that value from 6 to 10, we'd have exactly what we need, right? We'd be able to evaluate, and the integral gets you back to an original cost function, the c of 10 minus the c of 6. Feel free to pause the video and try this one on your own because I am confident you could take it from here. My humble advice is that you don't FOIL out and simplify. I think this one's a lot cleaner using U substitution since I see that q minus 4 inside the parentheses and a squaring outside. So this makes me think of letting u equal the innermost part of the function, let u equal q minus 4. Our side work was always to take a derivative, right? A derivative, we could call this the derivative of the u function in terms of the variable q, du dq. And it just equals 1, the derivative of q. So du actually equals dq. We could use both of these things. Take them back to the original. Let's see if this does get clean, like I was saying. So it's 3, instead of q minus 4, it's u squared. And instead of dq, we could sub in du. It's just a nice, easy integral for us, right? We'll integrate this term, and it'll be 3 over 3, so 1 u to the third, evaluated not from u equals 6 to 10. Be careful with these. From q equals 6 to q equals 10. Sometimes I just write that q in there to remind myself, oh, you got to sub this back in first before you plug the values in. So instead of u to the third, let's write what u equals. Q minus 4 to the third, evaluated from 6 to 10, and now it's just a plug-in, right? Let me move myself out of the way. So 10 minus 4 cubed, that's 6 cubed, because 10 minus 4. Minus 6 minus 4 cubed, that's 2 cubed that we're subtracting. 216, take away 8, you get 208. And what did we just figure out? It's easy to get lost in all the numbers and variables here. Well, we took a rate of change, we integrated it to get back to an original cost function, and this is the change in cost. I think dollars would be a great unit, and all these problems need units on the answer, but dollars would be a good unit for that. Okay, so not bad. I especially didn't think that the integral part of it was too bad. It was just like kind of organizing the wording of the question. There is only one part of number 2 in the setup that I think would be tricky that I would have to help you with. I think I want to start you on this one and let you take it from there. It says the resale value of a certain industrial machine. So I know when you buy a machine or you buy a car, you buy it for one price and certain items depreciate in value. So as soon as you drive a car off the lot, its value might go down. Well, this machine is decreasing in a trend over a 10-year period at a rate that changes. So I want to underline that rate that changes with time. And do they give us that rate? When the machine is X years old, here it is, the rate at which its value is changing. So we are given a rate of change here. You can choose whatever letters you want for the variables. Maybe here I'll pick V for value. So this isn't V of X, this is the rate of change in V of X. This is the rate of change in the value here. And I probably, in this case, if I'm anticipating that we'll be integrating it, I think it's easy just to bring the 220 into both parts. So I'll call it 220x minus 220 times 10, so minus 2200. So this can be a good derivative equation for starters. Now, does this last sentence give us kind of like an interval? I want to integrate from something to something. It actually does, but I think this is the tricky part. It says, by how much does the machine depreciate? By how much does the actual value go down during the second year? This is the key phrase, and the reason I wanted to take a little bit of a closer look at this one with you. So we want the change not in the derivatives, in the value of the machine. So we want V of something minus V of something. The question is, what are those somethings during the second year? So the experiment starts when 0 time has passed. And during the second year should be, well, actually, should be from the end of year 1 to the end of year 2. I want to subtract the value at the end of 2 years minus the value at the end of 1 year instead of 0. So this is actually an integral from 1 to 2, and that's what I thought was the trickier part. So we'll go 220x minus 2200. And this is where I thought you could pretty much take it from here. This is an integral with respect to x. Feel free to pause, finish the problem on your own. We could probably clean this up real quick. We want to integrate, right? No use substitution required this time. Integral of 220x, so 110x squared, minus integral of 2200, so 2200x, evaluated from 1 to 2. There's no tricks about it. We got to remember to put units on our final answer. 110 times 2 squared, so times 4, minus 2200 times 2, and we want to subtract what we get when we plug in 1. So 110 times 1 minus 2200 times 1. That all gets maybe typed into the calculator, and you get this negative value, negative 1870. And I know that is a dollar amount again, because this is a change in value that they're talking about here. It's kind of funny the way that I worded the problem. I said, by how much does it depreciate? So technically, the machine depreciates by positive $1,870. But if you left your answer as a negative, I would know what you mean here. The machine goes down in value by this amount. Let's look at the third one. Promoters of the Durham Fair estimate. Oh, the Durham Fair. I love talking about the Durham Fair. It's in Connecticut. They get some good, usually artists to perform, some good 4-H going on. They estimate that tea hours after the gates open at 9 a.m. I have a feeling this will come into play in a second. Visitors will be entering the fair at the rate of, here's our indication, and this is another indication, people per hour, that we're given a derivative value. How many people will enter the fair between 10 a.m. and noon? Okay, so we'll give this a try. This, I didn't have a good letter for this function. I wasn't sure if I should use P for people or E for entering. I just used F of T. I said F of T, or F, maybe I should say F prime of T, is the rate of change. This is what it is here, the rate of change in people entering the fair. This many people per hour are entering. What do we want? We want a difference in the amount of people that are coming in from 1 hour to another hour between 10 a.m. and noon. So I want a difference in regular f of something minus f of something else. And the question is, what do we put for those hours between 10 a.m. and noon? Well, noon is how many hours after 9 a.m.? It's 3 hours after 9 a.m. That's going to represent noon. And then 10 a.m. is only 1 hour after 9 a.m. So I want to use, instead of the numbers 10 and 12, I want to use the numbers 1 and 3, 10 a.m. to noon. That should do the trick. It should be an integral because we're given a rate of change here. So 1 to 3 of all of this, negative 4t plus 2 squared plus 54t plus 2 squared. And actually the first one was cubed. I messed that up. All taken with respect to t there. Feel free to skip through if you think you can handle this one. Again, I suggest you substitution, even more so with this question, because you've got that t plus 2, that's the innermost part of the function. We could probably knock it out here together. Let's do some side work. Let u equal your innermost part of the function, so t plus 2. And we'll take a derivative. Du over dt is going to equal 1. So du equals dt. And these go back into the original. This is great u substitution practice. We want to integral from t equals 1 to 3 of negative 4, how about we just say u cubed plus 54 u squared. Okay, and instead of dt, we can write du like that. Now's the time to integrate, so go ahead and give it a try. Negative 4 over 4, u to the fourth, so negative u to the fourth. 54 divided by 3, so plus, we'll say 18 u to the third. And we don't want to evaluate it from u equals 1 to 3. We want this from t equals 1 to t equals 3. That's the thing I sometimes forget, is I plug these numbers in one step too soon. But instead, let's plug back in. So instead of u, we're writing t plus 2. So negative t plus 2 to the fourth plus 18 t plus 2 plus 2 to the third. And that's evaluated from 1 to 3. Feel free to plug in 3, subtract what you get when you plug in 1. Really pause here and make sure that plug-in goes okay for you. All said and done, you get 1220. And what are our units here? This isn't a value this time. This is an amount of guests entering the fair. So I'm going to say people. Durham Fair is bustling during these hours because over 1,000 people are entering at that time. You'll see a couple more good examples on the back. I just want to give you a little pieces of advice so you can start them on your own. 4, you're going to be able to handle. It's not too bad. There's one added dynamic to 4, and it says something about the amount of bushels in a crop that are happening, and then also they're mixing in how much will the value change. So this just says, this first sentence says, it estimated that t days from now, a farmer's crop will be increasing at the rate of, so the crop is going to increase at this rate. I just called it, for a number of bushels, I called it B of t. So this would be B prime of t, the rate of change in the amount of bushels of the crop that are going to be produced. By how much will the value of the crop increase? This is really important. During the next 5 days, that's crucial. And then this we don't need to the end. I was worried about this $3 messing you up in the beginning of the problem. All we have to think about is this. Let me give you a few notes here. The during the next 5 days part is going to tell you your limits of integration. The value of the crop, we can do this at the end. We'll say value equals, well, I think about this logically, number of bushels in the crop, right? How much you have, times the value of each bushel. So price, we'll say, per bushel. Everything I'm writing in red here, I want you to save to the end, save till the end of the question. Because a good way to get started on this one is you're finding, this is a definite integral question, you're finding a change in, first, the amount of bushels, so b of something minus b of something else, and that'll take an integral from one value to another. During the next 5 days, well, logically, it just says over the next 5 days, so from when the experiment starts, so start at time t equals 0 in this particular question and go to the end of 5 days. So that's a good setup. This is my advice. Set up an integral from 0 to 5. Set that integral up of the rate of change that you're given. So 0.3 t squared plus 0.6 t plus 1. This one should not be bad for you to take at all, right? You'll get an answer. That's going to be a number of bushels that you get for this. And it's the increase in number of bushels. And then, last piece of advice, go back to what's in red. So take that answer and multiply by the $3 per bushel. If you take whatever answer you get here, multiply by 3, that should be your change in value. That's all you need the 3 for. And lastly, when you go down to look at the final question, I think you'll be fine looking for the wording that shows that this is a rate of change. I think I called this f prime of t. It seems like every single one of these problems has given us a derivative to start out with. And then just a piece of advice. As you're integrating that e expression, there's a good rule you can use. The integral of e to the kx, we've talked about this a little bit before, always comes out to be 1 over k e to the kx plus c, like that. You won't need the plus c in this problem because I have the feeling you'll be using a definite integral instead of an indefinite, but it does make the integration quicker, and I know you can piece through the wording of that. Any questions, let me know. Enjoy the rest of your day. Catch you on the flip side.